Let me start sharing my. Can you see my screen?
Yes, sir, we can see.
Yes, sir.
Good. So today's focus of this practicum is basically the theme of this GIAN course. Please remember that the course is not cyber physical system but smart physical system. Although we know that cyber physical systems themselves are smart, but how to make a smart system smarter is uh, one of the ideas of in terms of again the examples. Most of the examples into a smart system, and that's why the title of this talk is Intellectualization Opportunities. Okay, so how do you intellectualize, or how do you provide intelligence to system so that they can work on the opportunities, they can improve the smartness, they can improve the reliance, they can improve the resilience, and they can be also uh, meant to have a system which becomes more autonomous. Now, one very important point before I move forward, if you look at we also call cyber physical system as Industry 4.0. That is the fourth industrial revolution. And if you go through the history of industrial revolution, the first industrial revolution was more about mechanical power, mainly steam, hydraulic, and mechanical power. The second industrial revolution was about basically the electrical power, and the third industrial revolution was more about is my screen visible?
Yes, sir, it is visible.
Yes, yes, sir.
Okay, so I don't know where I have lost connection, but what I was telling about the major feature of the fourth industrial revolution is it's autonomous. That these systems are basically autonomous system, and this is the uniqueness of all the autonomous. I think you understand autonomous, that all these systems should be capable of behaving, controlling, acting on their own. Like for example, our institute, being a CFTI, similar to, for example, IITs, or similar to like even NITs, similar to like IIMs, they're all autonomous institutes. That means they can frame their own curriculum, they can start their own structure, and now with the NEP 2020, they can even and have their own policy to have uh, like foreign students. Only thing is that they have to like take certain approvals for recruiting the foreign faculty members. That also is going down the drain. That is the autonomous system. Only thing is that we have to depend on the government for the financial part, and that is also more or less very autonomous. You raise your demand, the budget, the government scrutinize the budget and give it. On the other hand, if you look at for example, state colleges, for example, another popular college in the city of Jabalpur is Jabalpur Engineering College, which is state government college. It used to be state government college, but now converted to autonomous. So they knew this better, that when they were state college, everything was controlled by the state government. So that's the importance of autonomy, and that's autonomy is being provided by the Industry 4.0. Now, in that autonomy, if you add the intelligence also, what is going to happen is that you have autonomy and you are intelligent also. That means you will be able to use the best possible uh, the things in the best possible manner, and that will make the cyber physical systems which are autonomous, which are 100% smart, but they will become smarter, and that's what we call as SCPS, that is smart cyber physical systems. So intellectual, what is the meaning of intellectualization? Basically, it means that any person, when we say that he is intelligent or he is using intellectualization, that means he has the capability of reasoning. Not that he or she is doing something at random, but the person used logic and reasoning to overcome any uncomfortable situation, to answer any question, to come out of any crisis, or to do any task. And it is basically a way to explain and understand negative events. So, for example, if a person A is due to person B, then person B will think, as an intelligent person, the person B will think, what are the possible reasons because of which the person A was rude to him. Then, if you look at the intellectualization or defense mechanism, the defense, and this is adapted from the work of intellectualization defense mechanism example, retrieved from this website. So this will have like projection, sublimation, repression, regression, rationalization, compensation, identification, displacement, withdrawal, sympathy. And by the adding of these elements, your defense mechanism will become intellectual. So coming to smart cyber physical system, we know that cyber physical system is nothing but where when you have a seamless integration of computation facility with physical process and keeping human being into loop and information technology also into loop. So in all cyber physical systems, we had embedded computers and networks which monitor and control. They monitor through sensors and they control through actuators the physical processes, mainly the feedback loops where physical processes and computation affect each other. Now, a key point of this system is the control of physical processes from the monitoring of variable and the use of computation intelligence to obtain a deep knowledge of the monitored environment, thus providing timely and more accurate decisions and actions. The growing interaction of physical and virtual worlds which lead to generation of some of the techniques which are intelligent. And these intelligent techniques will take the cyber physical system to next level, or which will open new avenues for the cyber physical system. And this type of cyber physical system which based upon the intelligent techniques have been raised to next level or one level higher are called as smart cyber physical systems. So basically, in a smart cyber physical system, we have there are a lot of input from the software. They also deal with big data, different data resources, normally big data, which is collected from the physical object in the virtual component. And on this, with the help of software, with the help of data resources, intelligent techniques are applied so that the real world processes and can be managed efficiently. And this type of smart cyber system can lead to new types of application and new types of services. And all these components of smart cyber physical systems have a higher degree of autonomy. I told you before this also that even cyber physical systems are autonomous, but smart cyber physical system has a higher degree of autonomy. And in this process, all these components they cooperate with each other in a uh, like uh, more robust manner, more stable manner, and they also have. Just give me 1 second. Is the system going live or not?
It is live.
Can anybody see this?
It is live. Actually.
I'm not able to see.
It is showing live. Actually.
Okay, that's fine. I'm not able to see. So, okay, it's showing here. Fine. So, this is like with this autonomy, these smart cyber systems can be robust. They can be scalable. That means you can make it for a small component. You can take it to larger platforms, and they're decentralized also. So, please understand, and you can look from the examples of your own academic institutions that a centralized system is relatively slow going. But on the other hand, if you decentralize it, that you give decision-making capabilities in different places, the system becomes leaner, swifter, and lit. Actually, it moves faster. So that's the objective of providing components autonomy and making a cyber physical system a smart cyber physical system. So overall, a smart cyber physical system is a complex engineered system. So normally we will employ the system for a complex process, which is empowered by the computing of cyber physical systems, and it must have, because it's a smart, because of this smartness, it will have capability of reasoning, learning, adapting, and evolving. It will reason out if X is happening, why X is happening. In the process, it will have self-learning also. It will learn also. It will adapt. From like central part of India, which is very hot these days, suddenly you have to go to Alaska or Siberia, where temperature is still in minus. You will immediately put on some warm clothing and you will adapt yourself. So that's the adaptation, and you have to evolve also. You have to keep on learning, reasoning, and you have to grow. It is something like a natural system which evolve. Like you, for example, you sow the seeds, and the seed will ultimately become a big plant, a big tree. That's evolution. And as an outcome of data-driven dynamic computing, reasoning capabilities, the adaptation, evaluation, the knowledge acquired during runtime, the non-linear and emergent behavior of cyber physical system, that's all is an open issue. Okay, open issue means it is still not resolved because it is all dynamic. It's a data-driven dynamic computing, reasoning capabilities, knowledge acquired during runtime, the system being non-linear, and the behavior emergence as the system goes on. This is all an open issue and normally not experienced for conventional technical systems. That's why I said that we normally engage smart cyber physical systems for complex engineered systems. Landscape of systems, and this work has been adapted. This slide has been adapted from a review of principles of designing smart cyber physical system for runtime adaptation, learned lessons and open issues by Tafkar et al. 2018. So if you look at this system, the system can be both natural and artificial. A natural system can be physical, biological, and mental. Which cognitive science is a very strong domain these days. When IIT Kanpur has started a program in cognitive science also. Artificial will have again mental, social, and engineered. Now, engineered can be technical. Engineered can also be cognitive. Engineered can also combine with social and become socio-technical. Engineer can also combine with biological and become biotechnical systems. Engineered system can also be combined with physical system and become cyber physical systems. So when these engineered systems are combined, they lead to, if not combined, pure technical systems, combined with social systems, socio-technical, combined with mental systems, cognitive systems, combined with biological system becomes biotechnical systems, combined with physical system becomes cyber physical system. Then, if you look at the social systems, they can be further classified as complex, non-linear, and same way, like for example, if you look at biological systems, They can be, when the biological system and physical systems are combined, it becomes cybernetic systems along with social systems. So when all these are combined, for example, physical, biological, mental, social, engineered, you can see all five arrows are coming down. It becomes a cybernetic system. On the other hand, if you look at like only physical, biological, uh, and engineered system, it can be a linear system also, regular system, where it's an ordinary system where integration of software takes place, or it can be complicated system where again software integration takes place. But whatever domain of interest is complex or non-linear system, because we are talking about implementation of smart cyber physical systems. So it can be of four types. It can be self-regulating and self-tuning. It can be self-aware and self-adapting. It can be self-cognizing and self-evolving. And can be self-conscious and self-reproducing. This has been told by Professor Imre Howard also. I'll also show these four systems in one of the subsequent slides. So, taking from the same reference, if you look this, we have functional and structural adaptation. We have operational strategy generation and application system operation model. So if you look at any system, we have a system set point, which I told you yesterday, which will activate system controller. Set point is basically in a feedback system, what you can say, the error. So what is desired and what is happening. Like for example, you set your AC. Maybe you see it's very hot. You set your AC at 24 degrees centigrade, while the temperature in your room is 40 degrees centigrade. The set point is to bring the temperature from 40 degrees centigrade to 24 degrees centigrade. So that will activate system controllers. Then you have effector networks, you have physical application of these subsystems, and you have sensor networks. So from effective networks, you give control input, you will go to system operation model. From sensor network, you will give measure output, which will also go to the system operation model, and then it will go to a performance evaluator, and from there it will go to the intervention planner. From sensor network, we also collect the runtime data and go to the augmentation system network. And the augmentation system operation model is a two-way loop connected with the system operation model. So this gives you awareness and learning from augmentation to system operation strategy, and from operation strategy to function structure of adaptation is behavior deviation. And these are all adaptive parameters. So what happens is that from here, the performance evaluation comes to intervention planner. It will give you control parameters, and this differentiation is leading to the system controllers, which will lead to control gains. So you can see this is relatively a complex system where arrows are moving in different directions. In fact, it is difficult to understand in the first look also this diagram, because some arrows are moving from top to bottom, some arrows are moving from bottom to top, some are both ways, some are moving from left to right, some are moving from right to left. You can see right to left, right to left. So this makes the entire system highly complicated. So what happens is that uh, if you look at the conventional cyber physical system, or even conventional control system, you have a physical system in process, you do sensing, and based upon sensing, you do actuation. So this is called the zero generation of cyber physical system. And this work is again borrowed from the same work, a review of principles of designing smart physical systems for runtime adaptation. But once this system becomes self-regulating and self-tuning, that means you regulate yourself. Like for example, uh, I'll take an interesting example, not interesting, but a very relevant example. Suppose somebody in your known circle has been diagnosed with diabetes. So we know that she or he has to cut down the sugar level. So one way is that the doctor prescribes some medicine and the patient takes insulin injections. On the other hand, the person can change his or her regime. So he becomes very fit. He does a lot of exercise, uh, eat only green food, cut down on the sugar level, and take care of his or health very, very consciously. That's what we call as self-regulation. And self-tuning is when you tune yourself as per the situation. Okay, you adapt yourself. Not adaptation is one level, so you're just tuning. Like you tune the radio system to collect the FM channel. Okay, you search it, the system to find out. So that becomes, so if your cyber physical system has a self-regulation and self-tuning, it becomes first generation system. And second generation system will have self-awareness and self-adaptation also. And these second generation cyber physical systems are basically what we call as a smart cyber physical systems. We also have we also talk about third generation and fourth generation systems. The third generation systems have self-cognizance. That means they function more intelligently. The brain part comes into picture, and self-evolution. That they start evolving also based upon the changed circumstances. And the fourth generation system is self-consciousness and self-reproduction. So this side, from 0 to 4, the level of intelligence increases from self-regulation to self-awareness to self-cognizance to self-consciousness. And this side, the organization increases, that you control, this is you yourself control on the organization, from self-tuning to self-adaptation to evolution to reproduction. But third generation and fourth generation system are still in the research phase, not actually implemented. Even the second generation system are not fully implemented yet, but yes, we talk about them very vividly. We want to implement, and that's why we call it smart cyber physical systems. Okay. Then we have, so reasoning model, again borrowed from the same thing. If you look at the reasoning model, we have designing of smart cyber physical system, which is second generation of cyber physical systems. It is like a autonomous and self-organized units, and we have systems, self-awareness, self-adaptation. It is smartness and self-awareness of building blocks, middleware platform. Then we have methods for resilient and fault tolerance operation, real-time monitoring, self-healing, runtime self-control, runtime validation, several levels of control loops, distributed control, hardware redundancies, dissimilarity, installation, segregation, and production. And on the bottom, we have formal methods for smart cyber physical system development, which will include methods for modeling, simulation, and testing, patterns for and reference models for self-adaptive systems. And we have platform and for fast and reliable system development based on self-learning and adaptive methods with feedback control loops. So if you look at this house, so this house is basically reasoning model, which will be take into account the methods and principle for designing smart cyber physical systems. The smart cyber physical systems are the systems that must be designed to be self-aware and self-adapting. And this entails that they change their behavior and performance to adapt to new operational circumstances and opportunities through their life cycle. Then we have the theory of adaptation. The theory of adaptation is basically adaptability, which will be realized through feedback loops, and it's a key requirement to deal with uncertain operating conditions in cyber physical systems. And in this case, we have in engineering, we have the definition of adaptability, which refers to systems' ability to cope with threats while maintaining its parameters within certain previously set reference values. Like for example, you have to maintain the communication latency and reliability within smart grid. You remember we discussed briefly about the electric systems within smart grid, which is subjected to increase additional communication and processing loads caused by denial of services attacks. So if somebody is attacking your system, the system should be smart enough. The system should be able to adapt based upon the feedback loops to have the communication latency, so that your grid will become smart. And in this process, the additional loads which are coming by these DOS attacks, they can be countered. Then we also talk about significant advances in the engineering of both hardware and software system, which have led to the concept of what we call self-adaptation. So when we add self before adaptation, it basically means the system is autonomous, what I started with. So it's not that somebody else is controlling you, but you yourself is adapting yourself. And so this will be, the system will become autonomous, and the purpose is to adjust to changes that occur in its context and environment. And whenever an error is detected, the design, which includes the logic for recovery and correction, it will take action to adjust the operating voltage and correct that result. So, like for example, when some fluctuation is happening, like for example, I take a practical example. Like most of you must have faced in your home's power fluctuations, and sometimes it become very rapid, which may lead to the electronic appliances going bad. So if a self-adapted system will automatically adjust the operating voltage and will make sure that the pulses which are going to electronic devices, they're not harmful. So the smart cyber physical system must be context aware. They must be partially or fully self-managed, and therefore they must use of relevant services to capture the environment status and operating conditions to assure the expected behavior in all scenarios. And they must also evaluate the cyber physical systems are inherently feedback systems because besides assuring predictability, they also depend on the application domain, and for that they must be they must be adaptable. So basically, the at the backbone of all feedback system, and if that feedback system is smart, so that based upon whatever values are being predicted, you remember I gave you the example yesterday also that a conventional system will go back and then rectify it, and a smart system always predict, and this difference between it. So if you periodically keep on inspecting, you avoid that state, and they predict what is going to happen in future, or what is going to happen immediate future, and take corrective action so that to prevent that happening. Then coming to self adaptation. So self, as I told you, and the word self means it's autonomous, and this autonomy is reflected across all three architectures, which we have discussed earlier also. It will be reflected through physical architecture, network architecture, and cyber architecture, and can be implemented through action taken based on simple logic reasoning or driven by knowledge extracted from big data analytics. So for example, when you talk of a wireless sensor, the wireless sensor can obviously adjust the rate of reporting depending upon what power inputs it is getting by simply changing the sleep time intervals, and it happens when the energy level increases some threshold values. So that if there is any like for example, today what was happening in an early part of the lecturing, so there were some losses of the like data packets. So a smart system will take care of that and remove the percentage of data loss, so that if the error goes up, it automatically come down as fast as possible. So what is a objective is to design a novel and complex system. So such novel and complex systems should be self-adaptable, which means it must include efficiency and performance. It must be flexible. It must be reliable and configurable. Not only configurable, but should be reconfigurable also. It must have some functionality, interoperability, dependability, security, scalability, composability, mobility, as well as self-adaptation techniques. And one model which talks of this self-adaptation techniques which are adapted or which are designed for cyber physical system is called as the MAPE model, which stands for M stands for monitor, A stands for analyze, P stands for plan, E stands for execute. So monitor, analyze, plan, execute model. This model, as we say, monitor will depend upon the feedback control, analyze will depend upon the agent and self-organizing techniques. Planning will depend upon control theory methods and possible combinations. Let's see how the MAPE model works. So the four components of MAPE model is monitor, analyze, plan, and execute. So monitoring means, so it must have mechanism for collecting, aggregating, filtering, and storing information. And all such information must be collected from the environment, open source, through sensors, and must be stored in a database. Now, this data must be analyzed. And for the purpose of analysis, the system must see whether adaptation is required or not. Like, for example, you are traveling from a hot environment to a cold environment. So you have to adapt. So this needs to be checked. And if the adaptation is required, some triggering of action should take place. How the triggering will take place? The triggering will start from the planning. So it will not be default run, it will be you have to plan something. So you have to plan, you have to initiate an action plan, which is basically selecting the adaptation policies, which is needed to achieve the system's goal. And then it is finally execute. So our post planning, the system must control execution of the selected adaptations plan through actuators. So instead of using standard database, this model uses a knowledge database to store collected data and along with adaptation goals and what are the different states which are shared by the MAPE component. This is a component of MAPE. You can see this is adapted from the work of J. Delhi et al. Self-adaptation techniques in cyber physical systems. So you have monitor, analyze, plan, execute, and then you have a knowledge, which generates the ontology. So you have this is your database. From this data, you monitor, like you have acquisition agents and your filtering agent. Analysis agent analyze, planning agents plan, execution agents execute. And everything is connected to internet, sensors providing some information, and then some actuators give you the control action. So this is your physical layer. The middle one is a network layer, and the top one is a cyber layer. So from the physical level, sensors give information to the internet. The internet gives some command for the controlling. We also have mobile users with mobile devices which are connected to Wi-Fi, and from this signals goes to the cyber layer. Internet also gives to cyber layer, and from knowledge, the information come back to the user or data from database, the information comes to the internet, and then some action is being taken. So this is like how your MAPE model looks like and functions. The components of MAPE model are, as I said, monitor, analyze, plan, and execute. And you can see in every stage, the knowledge is augmented. So ontology is created, so this becomes a managed system. So you have a managed system, you have a managed, this is a managed system with white box. The gray boxes are this managing system, and these are all interaction. So this is a similar work to this, Okay, let me share again. Okay, so this is the mapping model, which is borrowed from the work of Ross et al. And their work is titled Self-Adaptation Techniques in Cyber Physical Systems. So they also talk the similar thing: physical layer, network layer, and cyber layer. In the physical layer, we have self-adapted operation based on context. In the network layer, we have dynamic routing based on adaptive controls, and which adapt the communication within the CPS. And in the cyber, we have to adapt the behavior of the entire CPS, where agents they have MAPE, they can adaptive control algorithms. So this and you can see this becomes a circular from physical to cyber, from cyber to physical. And then any question in this before I move to the next model? Anybody has any question, any comment?
No, sir. No, sir.
No? Okay. So next model is what we call as a mass model. Okay. This recording is stopped. Vijay, are you recording?
It is showing recording.
In my end, it is not showing, but it is asking.
It is.
So probably you have become host. That's why it is changing.
Yeah, it is showing.
So no issues. So mass is basically a multi-agent system. So before going to a multi-agent system, you must understand what is the agent. So these both agent and multi-agent that represent a new paradigm, which is mainly useful in a autonomous implementation of feedback control system, so that this system becomes self-adaptable, and that too for a complex, large-scale, software-intensive engineering system. Now, most of these systems are developed for the software sector, because you know that for the last many years, the software systems have become very complex. The same level of complexity is very difficult to be replicated in a physical or engineering system. So multi-agent systems, they basically they are benefited from their characteristics that they have because they are multi-agent, they have a good communication protocol, they have a good negotiation protocol, and they have the good learning methodology also. Because all these multi-agent systems are primarily goal-oriented systems, and they follow approaches which are goal-oriented, so that the entire system can be autonomously adapted to environment at runtime. I can take again a very simple example. Like for example, when you are traveling, the based upon the GPS, your coordinate changes. If you are traveling from one country to another country, in your mobile phone, the time also changes automatically based upon the GPS. So the system is adapting, software is adapting. It's not that you have to manually adjust it. In non-smartphones, we have to do it manually, if you remember. But in smartphones, it automatically does the same, and it basically take care of these things based upon how does the system behave, or what does it look like when you talk about in the in the runtime. Basically, the importance is it's not something like you are driving the car and something is you are, say for example, you suddenly note that the petrol is low in your car, so you go to a petrol pump and get the gas from the gas station, get your tank filled. But a smart system is something like you must have seen or read stories that aircraft filled in the air. Same way when you are driving a car, the tank of the fuel, the tank of the car gets filled by the fuel. That's a that becomes a adaptable system, a runtime adaptable system, and that lead to autonomous systems, or that leads to autonomy to the systems. So in addition to this, the multi-agent systems, the primary characteristics are uh, we know that they have autonomy, cooperation, reactivity, proactivity, and because of which the multi-agent systems are suitable uh, as different entities are capable of reacting to external events by adapting to the behaviors, and based upon the inputs which they're receiving from the environment, they become capable of taking informed decisions. So it's not decisions which are taken in a hurry or based upon just some feedback. So the feedback is analyzed, like it's like something what we do in the mapper system. So whatever information is being asked, that is analyzed. That leads to what you call an informed decision. So decisions are taken based upon the proper information. It's not something out of blue. It's not something like you are driving and you find a blind turn. You don't know what is going to come ahead of you. It's something like you have mirrors placed, and based upon the mirrors, you can see which type of vehicle is coming from that blindfold. So the generic mechanism of achieving self-adaptation is the data collection about the system state, enacting changes in the environment and context, analyzing and extracting relevant information. For example, what are the trends or what are the systems? Based upon that, it will be decision making and taking adaptive actions. So basically, a self-adaptive system consists of two parts, as I showed you here also. The first one is the managed system, and second is the managing system. So these are the gray boxes are managing system, the white boxes are the managed systems. So it is the managed systems, which is basically system layer, and it is also called managed resources, base level system, or target system. And this managed system basically deals with the domain functionality. And the second is managing system, which is called as the architecture layer. So this is system layer and this is the architecture layer, which have which is also called an autonomic manager, self-reflecting subsystem, or controller. And this managed system is basically responsible for adaptation of the managed system to achieve particular output, particular quality goal. And for example, if you go back to this image, so monitor, analyze, plan, and execute, they manage the managed system and make it behave the way that we want to have it. And in the process, it creates a knowledge. So in the runtime, not only system is managed, but even the knowledge is also collected and accumulated. Then what is based upon that? The next question comes is what is self-adaptation management? So as I told in the beginning that CPS are by nature self-adapted. So they are because they're required to use feedback loop mechanism to deal with various uncertainties, control their emergent behavior, and they have to be resilient to change. So whenever you're adapting a CPS, it has to be in a cross-layer concern where the whatever solutions are coming, that must combine different layers, different adaptation mechanism within the cross layers. So that means in a CPS system, we have multiple feedback loops, and as the system becomes more and more complex, the number of loops will increase, but most of the loops are still applied in the application layer, not in the system layer. So performance, reliability, interoperability, and security are the major issues which CPS has to be worried about, mainly if it is looking for self-adaptation management. There are a few other challenges also, like for example, how to map concerns to layers and adaptation mechanisms, how to coordinate adaptation mechanism within a cross layer, and how to ensure system-wide consistency or adaptation. So whatever terms we are using over here, that seems to be very simple, but they are difficult to be applied or particularly applied in practice. So this leads to what we call as how do we create smartness? It is something like when like most of these students enter into a BTech profession engineering stream, they have just moved out from the school level, which is more like a spoon-fed system, and when they enter into a decent institute, they are taught how to learn, they interact with their friends, they are given independence, they are given autonomy, they're out from their families, and they become smart. So that is what you call smartness creation. How do you create a smart? Same way in a cyber physical system also. So I'll take Same example, some of the examples which we have discussed earlier also, but we'll talk from the perspective of how do we create smartness. Like for example, this image we have discussed, I think last to last lecture when we talk about the CPS exemplified. This is a traditional factory where all these orange color boxes are uncovered area. They are not network, they are not connected. But once you go to a smart factory, so all these are connected. So how these are connected? They are connected by data, and they are connected by the data which are linked to the coverage area. And we normally add some devices also in the process which collects your big data. So all the environmental factors are also taken into account. In this case, you can see environment is not connected at all to the system. So when you connect all these devices through internet, through data, to a server, and when server takes smart decisions based upon the changing parameter, like for example, if temperature is going high, it will cut down on temperature. You remember yesterday I have taken a example where the distortion of additively manufactured components will be reduced by managing the temperature. So that is the conversion of a traditional factory to a smart factory, or making or imbibing smartness into a factory. Same way, let's take the example of a home. So we know, like this is taken from Smart Home 101, how to get started with home automation. So this is your traditional home. And if you start collecting data and you start taking decision, mainly if you have a software which will take collective actions on its own. Like for example, suppose I take a very simple example. Uh, Suppose you're not back home, and it has become evening, something like 6:30, and the outside environment has become dark. So based upon the sensor, which will sense the level of light or brightness in the outside, and maybe in some of the rooms, the lights will automatically switch on maybe at 6:30, 6:45. You are not controlling. You can also control. So this becomes a self-adaptive system. And that's how you are inculcating smartness into a traditional home and making into a smart home. Like for example, you know that the based upon the level of laundry, the washing machine will automatically take decision what level of washing it has to do. It is like hot wash, normal wash. If it put a woolen cloth, the washing for the woolen clothes. So this level of smartness, this level of decision making is not taken by you, who is in a remote control, by the software in the system. That becomes a smart home. Healthcare also we have discussed in the first tutorial, where you talk about medical care by having different factors connected to each other. So you have, for example, from diseases to nutrition calculation, from pocket doctor to heart rate monitor, everything is synced with a smartphone, which is controlling the body, making the SOS call, doing research, and even the remote consultation from the doctor also. So you are maybe integrating a hospital with different parameters, the parameters about the patients, the input from the doctors, the input from the different devices, and output to those devices. If you everything is network with the capability to take decision based upon the feedback and capability to adapt, that becomes a smart cyber physical system, what we call as second generation system. Smart city, again, the same example which we have taken in the first lecture. So all these factors, whether you talk of industry, security, retail, society, healthcare, home. So whatever input is coming, that is leading to actuation of the sum of the feedback controllers, and based upon those feedbacks, the system is taking decisions on the runtime. If first, like for example, uh, suppose you are driving a car and your car is smart, and even the road on which you are driving is smart. So somehow you get a message that 5 kilometers ahead of you there's a road blockage because some boulders have come and has been dropped on the road, because of which there's a road blockage. So it is better to take a uh, turn a bypass which is going to come maybe in 200 meters ahead of you. So what is going to happen? If your road is smart, the transportation system is smart, and your car is smart, you will immediately take a turn 200 meters ahead of you and avoid that road blockage. Otherwise, we would have gone up to that particular point and maybe stuck in the jam. If you have been lucky, you could have been able to take a U-turn, come back by 5 kilometers, and then take a turn. So 5 kilometers going, 5 kilometers coming back. This is small example. It can be 15 kilometers also. So you are not only saving a lot of fuel and time, but you're making your journey also pleasant and comfortable. Then this is somewhat slightly newer example. We have talked about agriculture, but how do we create smartness in the agriculture? So you see, we have, for example, agriculture site 1, agriculture site 2, and agriculture site 3. So in the agriculture site 1, which is this one, we have an energy generation system, which is renewable energy with solar panels. We have a local monitoring and control center. This is like the crops which are created in the greenhouse effect, controlled environment, and all these crops lead to generation of some signals. They lead some data which is collected to internet. And you have, for example, a system which works on the based upon the sensors. It find out the moisture content of the soil, air temperature, and humidity in the air. It also talked about the leaf wetness through a wireless leaf wetness sensor, the soil temperature. You also have a IP66 rated sensors. Then you have weather protected enclosure. You also this is weather protected enclosure. You also have a motor which is wirelessly actuated, and all this is you can see data which is transmitted to this cloud where the data will be analyzed and serviced. Same way we get the data from the site 2 also and site 3 also. And then we can have a base station. Data we have already discussed, we get it from the Ethernet or Wi-Fi. We can also have a cellular Wi-Fi gateway. And this analysis is controlled on its own, or you can have an owner or supervisor who helps in taking decision. So this leads to creation of or imbibing of smartness into the agriculture system. And this work, as you can see, is adapted from the smart fiber filter system for control environment agriculture. Same way we can work on the energy management system also. This we have discussed in the last lecture, so I'm not repeating this again, complicated circuit. So then we talk about development of feasible solution ideas based on function representation analysis. So the purpose of this is to understand what is functional model. The functional model is used very widely by the software sector, in computer science particularly, and it is basically talks about the activities, action, processes, operation within the model system or system area. And a functional model, which is similar with the activity model or process model, is a graphical representation of enterprise function within defined scope. And the purpose of the functional model is to describe the functions and processes, which is meant to assist with discovery of information needs and to help identify opportunities and establish a basis for determining product and service costs. This is how it works. And this work is adapted from example function model of processes taken from this site. So you can see that there are 4 sets. The first is remove and replace, then schedule into shop, inspect or repair, monitor and control. And you have inset assets, you have spare assets also. You either replace or repair. You can also, this will help you in, this differentiation will help you in identification of malfunctioning, which may lead to replace asset. This is asset before repair, and when you're going for repair, the parts supplied, and these are assets awaiting report, again monitor report, and assets after report. So everything is network. So this type of model is called function model because it is functional model, sorry, which is based upon the different functions. What function are you going to do? Are you removing or replacing? Are you scheduling into a job? Are you inspecting or repairing? Are you monitoring and routing? So the functional representation model must meet three conditions. The first is that it should be capable of completely expressing the requirements of the product design and should not lose any information in the design process. The second is it should be convenient to realize the mapping and transformation process to behavior and structures. And third is it must have the function representation, which with it must constrain information also. So in the software, we call a software development lifecycle SDLC, but similar concept is also included in a product development cycle or product lifecycle management cycle. Product lifecycle management cycle is with the product development, the top of any product development, but mainly from the software part. So, for example, you are developing a mechanical product, the software aspect of that product in terms of CAD, CAM, CAX. So those softwares are used there. So it covers detailed plan for building, deploying, and maintaining the software, and it will include the complete cycle of development. All the task of planning, creating, testing, and deploying a software product. So as I told you, this concept is very widely implemented into the software development cycle because softwares have become very complex. So they are using it, but it is also being used in the physical product development also. What we call the product development life cycle, PLM or PDM, product life cycle management. So there are different types of development life cycle, which is used not only as SDLC, but a product life cycle management also. These models are waterfall model, V-shaped model, iterative model, spiral model, rational unified process, Scrum model, extreme programming model, and Kanban model. Now, please understand before I tell you very briefly, time is also running out, what all these models are about. Please understand that whenever you are developing any product, whether it's a tangible product, physical product, maybe a car, maybe a pen, maybe a pencil, maybe a all pin, or maybe a software, there are certain stages. The stages are need assessment, problem identification, concept development, then concept assessment, okay, then embodiment development, and then basically the product development or cycle. So all these stages are same. How they are placed in a software development process or a product development process will differentiate between different models, from waterfall model to V-shaped model to Kanban model. So this is like stages. You have requirement analysis, design, implementation, testing, deployment, maintenance. So we'll have all these 6 stages in all these 7 models. So in a waterfall model, from output of, you can see this looks like a waterfall. So from one to another, from second to third, from third to fourth, based upon the requirement output will have design. From design to implementation, from design to implementation to testing, testing to deployment, deployment to maintenance. And everywhere, the purpose of why we call the waterfall model is that at each stage, we have a check. So it is something like if waterfall is coming and you have different, like in a mountain, you have different stages. So water will come, stop at design, stop, will fall, stop at implementation, fall again and stop at testing, again fall, stop at deploymentation. So this is a waterfall model. Then the V model, again we have requirement analysis, system design, architecture design, model design, coding, unit testing, integration, system testing, architecture. But all of them are linked somehow, like for example, requirement analysis and acceptance testing goes for accept test design. So when you start software creation and when you launch, you do the acceptance testing. When you launch system design and with system testing, you go for test design or system test. When you go for architecture design and integration testing, you do integration test design. When you have module and unit testing, you go for unit test design. And in between, you have this is pre-coding, this is post-coding. This is iterative model. You go for planning, implementation, design, and then these steps, detailed design, development, testing, delivery, you keep on repeating. Like most of the software, most of the complex system like car design, transportation design, for example, system design for the metro train, it is iterative in nature. So you keep on iterating. So these 3 stages are, 4 stages are constantly iterated until you land to correct stage. And as mentioned, all these are borrowed from the work of the 8 software development model: slice, dice, and organize in charts. Spiral model. So we start with determination of objective, narrative, and constraint. So this is start. Go for risk analysis, prototype 1 development, concept development, requirement plan. Again, risk analysis. So you have second stage risk analysis and alteration evaluations. Then prototype 2, software analysis, validation, development plan. Again, risk analysis. Prototype 3, software design, which leads to development of variables, validation and verification, integration planning, again risk analysis, then operational prototype, detailed design, coding, unit testing, integration testing, uh, acceptance testing, and release of the software. And this lead to the planning of the next iteration design. So you can see this is a spiral mode. Before this, rational unified process, RUP. So you have all these phases: business modeling, requirement, analysis, design, implementation, testing, deployment, iteration, on different stages at inception, elaboration, construction, production. And you can see they have different variability. Like for example, business modeling is highest at inception. Requirement is also higher at the level of inception and elaboration, then goes down and again come up, again goes down, again come up. Implementation is slowly increases, becomes a plateau, what is called as a implementation phase. During this is the start of the product life cycle. This is a maturity phase, and over here the product life cycle is over. So product starts dying down. So you have to come up with the next version, or you have to improvise your model. Testing initially less, and as your system becomes old, you have to keep on testing. And deployment is maximum after this stage, after construction testing. So you can see you have one stage of inception, two stages of elaboration, three stages of construction, and two stages of transition. This is Scrum model, which is like something like circular going ahead. Then again, so you have like multiple sprints, and every sprint will have plan, design, develop, test, and deployment. So you'll do one, review, do it again, review, do it again, review, do it again, review. You keep on doing it depending upon what type of product you are doing. So every stage, you will have like short one, not very longer one. So very shortly, you'll do in a period of 2 to 4 weeks, plan, design, develop, test, deploy. Review it, again do it. And you can keep on doing it till you are satisfied or till the product dies down. And the extreme programming will have like iteration planning of pair programming, collective code ownership, code standards, test-driven development, continuous integration, your acceptance test and release of the software. And the last is Kanban model, where you have backlogs, what to do, in progress, testing, done, block. And you can see you have different features, bugs, which you do in all these work. What are the backlogs? What do you have to do? What is in progress? What do you have to test? What is being done? What is being blocked? Okay. So that's all from my side today. Any question? We can quickly take some few questions.
Hello, sir.
Yeah.
Sir, are these models are related to each other from start to end?
Yeah, please speak.
Sir, yes, sir. My question is these models are related to each other from waterfall model to the last model?
Okay, let me answer this in this way. That basic purpose of all these are the different stages of product design. Now, this product design phase is applicable for physical product also. As I said, it is applicable for this pen also. It is applicable for this mouse also. It is applicable for this mobile phone also, and it is also applicable for uh, uh, software also. Now, how these stages are implemented or executed will make to different models. Like they will lead to whether it's a waterfall model, a V-shaped model, iterative model, or Kanban model. So all will you can see all these are stages, and how these are like they are once or they are iterated. They goes in a spiral manner or the waterfall manner. This is the way with differentiates between them. Am I clear?
Yes, sir. Clear, sir. Clear. Thank you, sir.
Keshav, am I clear?
Yes, sir. Yes, sir. Very clear, sir.
Thank you.
Thank you, sir.
So if no question, I can stop sharing, and we can quickly take another image, another screenshot, and then close today's session. So please switch on your cameras quickly. The later you do, the later will be time to say goodbye. Professor Gupta, your camera is not on. Thank you. And I couldn't see Abhineet and Anil. I am not here there also. Anil and Solia. Yes, your hand is visible, don't worry. So don't text anything, we will come. Okay. Okay. So I'll take one snapshot and just will close. Say cheese. Thank you very much.
And tomorrow, actually, we will be having hands-on, so it is your turn, participants' turn. So whatever you had learned, you have to apply and then try to devise something in the practical case.
Sorry, please come again.
Tomorrow they will be practicing basically, so they will be taking some problem and then they will
I'm sorry, I don't think what has happened.
there is some problem at your end.
Even my camera is also not coming. So I'm sorry if you are there. Please, can you just switch on your camera once again? Image was not recorded. I don't know if there's some problem at my. There's loss of data packets actually. Please switch on your camera. Have you taken the image photograph?
Yeah, I had taken one.
I'm lost. Vijay, have you taken the image?
Yeah, I had taken.
Okay, then you can share it. I'm not.
Yeah.
I'm just. Any other thing you want to say to the participants?
No, I was just telling them that tomorrow they have to practice actually.
Yeah.
So far it is lecturing, but tomorrow will be there.
Whatever we have been telling you now, you have to apply so that you can learn more.
Right.
That will start from tomorrow actually. The purpose of this course, the design of this course was meant to have, so that if it had been in campus, would have asked you to do with hands-on. But since it is done in a remote manner, so what best we can do, we are trying to do. Okay, so I'm just closing this session. Vijay, you have the rights.